Light is supposed to be the ultimate speed limit. Nothing outruns it. Nothing even comes close. And yet, even at that speed, the universe is still wildly out of reach. The nearest star, years away. The galaxy, longer than human civilization has existed. By every rule we know, we're stuck. But here's where things get strange. Some scientists aren't trying to go faster than light anymore. They're trying something far more radical, changing how distance itself works. Because if you can't beat the speed limit, what if you make the journey shorter instead? That idea, once dismissed as pure science fiction, is starting to take shape in real research. Not engines that push harder, but concepts that reshape space. Not breaking physics, but bending it in ways we're only beginning to understand. Early models are getting sharper. Energy demands are shrinking. And for the first time, there's a serious conversation happening about a completely new way to move through the universe. Not faster through space, but differently with it. If this works, it wouldn't just be an upgrade in speed. It would be a new way to travel beyond light speed itself. Every atom in your body was forged inside a star that exploded before our sun existed. You are made of ancient stellar debris. The iron in your blood was cooked in the core of a dying giant and scattered across the galaxy before gravity pulled it into a new cloud, a new star, a new world, a new you. You are not in the universe. You are part of it. And that universe, the one built from the same material as your hand, has been telling you for a century that you cannot leave. The nearest star beyond our own sits 4.2 light-years away. At the fastest speed any human object has ever achieved, a journey to that star would take 73,000 years. The civilization that launched the ship would be gone before it arrived. The language spoken at liftoff would be as foreign to the receivers as ancient Sumerian is to us. Yet the people inside would be dead 10,000 generations before the destination came into view. That is the wall. It is not a wall of technology. It is a wall built into the geometry of reality itself. Einstein constructed it in 1905, and for 120 years it has held. Nothing with mass reaches light speed. The faster you go, the heavier you become. The heavier you become, the more energy you need to go faster still. At light speed, your mass becomes infinite. Infinite mass requires infinite energy. The universe does not offer infinite energy. The wall stands. And then, in 1994, a physicist named Miguel Alcubierre did something that nobody expected. He did not break the wall. He went around it. What he found inside Einstein's own equations using Einstein's own mathematics is the most dangerous, most beautiful, and most civilization-altering idea in the history of physics. Not a vehicle that goes fast. A vehicle that makes fast irrelevant. A machine that does not move through space at all, but instead carries space itself. If this reaches you before it feels real, that is correct. Stay with it. We begin. The number 4.2 light-years does not feel like a wall until you understand what it means in terms that human experience can reach. Light travels at 299,792 kilometers per second. In 1 second, a photon crosses the distance from New York to Los Angeles 8 times. In 8 minutes, it crosses from the sun to the earth. In 4 years, 2 months, and 11 days, it crosses from the sun to the nearest stellar system. Alpha Centauri, a trinary system 40 trillion kilometers away. Yes, the fastest spacecraft humanity has ever built is the Parker Solar Probe. At its maximum velocity, it reaches approximately 690,000 kilometers per hour. That sounds extraordinary. It is extraordinary. It is also, by the standard of what crossing interstellar space requires, essentially motionless. At the Parker Solar Probe's top speed, a mission to Alpha Centauri would take approximately 6,300 years. The Roman Empire fell 1,600 years ago. Written language is 5,000 years old. At our fastest, we could not reach our nearest neighbor in the span of recorded human civilization. Alpha Centauri is the closest possible destination outside our solar system. And it is not particularly interesting. It has planets, but none confirmed as habitable. If you wanted to visit a world with genuine potential for Earth-like conditions, Now, you would need to travel further. The nearest truly promising candidates sit tens of light years away. The nearest confirmed exoplanets in a zone where liquid water could exist on the surface are mostly between 10 and 50 light years distant. At the Parker Solar Probe's velocity, reaching the closer ones would take between 90,000 and 450,000 years. The entire history of anatomically modern humans on Earth spans roughly 300,000 years. Go further still. Our galaxy, the Milky Way, stretches approximately 100,000 light years from edge to edge, end to end, side to side. A beam of light takes 100,000 years to cross it. There are somewhere between 200 billion and 400 billion stars inside it. At any reasonable fraction of light speed, crossing the galaxy takes longer than complex life has existed on Earth. The Milky Way is not a destination. It is a prison sentence measured in geological time. The observable universe spans 93 billion light years. It contains 2 trillion galaxies. Every direction you look, in any patch of sky, there are structures whose light has been traveling toward you since before the Earth formed, and they are still too distant to reach in any human lifetime, in any civilization's lifetime, perhaps in any timeline that matters to beings made of biological material with finite lifespans. The cosmos is not just large, it is locked. Every star beyond our own is behind a door that the laws of physics, as currently understood, seal with an absolute permanence that is more final than any material wall. This is the problem that Miguel Alcubierre sat with in 1994. Not the engineering problem, not the funding problem, not the political will problem, and the physics problem, the reality problem, the problem that the universe itself seems to have been designed with an exit clause that prevents any sufficiently complex civilization from spreading beyond its home star system. He was not the first to think about it. Rocket engineers had been doing the math for decades and arriving at the same conclusion. Chemical rockets are hopeless. Nuclear pulse propulsion, which involves detonating nuclear bombs behind a spacecraft to push it forward, could theoretically get a ship to perhaps 10% of the speed of light. At 10% of light speed, Alpha Centauri is 42 years away. That is a human lifetime. That is almost within reach. But 10% of light speed requires a spacecraft mass that is mostly nuclear bombs. Estimates run into the hundreds of megatons of fuel for a small payload. And at that speed, a collision with an interstellar dust grain delivers the energy of a small nuclear weapon. The galaxy is not empty. It contains gas, dust, and microscopic particles at densities low enough to ignore at rocket speeds and catastrophic enough to matter at 10% of light speed. Laser sail concepts push photons against a reflective sail. Robert Forward in the 1980s calculated that a laser array with the power output of 10,000 nuclear reactors could accelerate a gram-scale sail to 10 or even 20% of light speed. The engineering requirements are so far beyond current capability that they are measured not in engineering challenges but in civilizational challenges. The array would have to be larger than many countries. It would need to operate continuously for years. It would represent a construction project larger than anything humanity has ever attempted, to send a gram of material on a one-way journey. And none of these approaches, not the nuclear pulse drive, not the laser sail, not any propulsion concept based on carrying energy from a home system, gets you to the stars in a human lifetime without turning into a project so vast it consumes most of a civilization's resources, to produce a vehicle that arrives at a destination with no way back and no way to slow down. Alcubierre understood all of this. He was a graduate student in Wales in 1994, not a senior professor at a prestigious institution. He was not heading a major research program. He was watching Star Trek. He has said in interviews that the show's warp drive made him wonder whether something like it was mathematically possible inside real physics. Not hand-waved science fiction, but an actual solution to Einstein's field equations. He spent time working through the mathematics, and what he found was not what anyone expected. The answer was yes. But the answer came with a price that made it simultaneously the most exciting and most terrifying development in theoretical physics since Einstein himself. Einstein's special relativity does one thing very clearly. It says that no object with mass can be accelerated to the speed of light through space. and the energy required diverges toward infinity as velocity approaches the cosmic speed limit. This is not a guideline. It is not an approximation. It is exact. It holds under every experimental test ever performed. But Einstein's general relativity, the deeper theory that describes gravity as the curvature of space-time, says something more interesting. It says that space itself is a dynamic medium. It can curve, it can stretch, it can compress, it can expand. And the expansion of space is not subject to the speed limit. Space does not have mass. Space does not have momentum. Space is the stage on which the speed limit operates, and the stage itself is not constrained by the rules that govern the actors on it. You have already seen this in cosmology. The observable universe is 93 billion light years across, and the universe is only 13.8 billion years old. Light travels at 1 light year per year. If nothing can travel faster than light, how can the observable universe be 6 times larger than light could have crossed in its entire history? The answer is that space itself has been expanding. Distant galaxies are not moving through space away from us at speeds faster than light. Space is growing between us and them, and that growth is not subject to the relativistic speed limit. The galaxies themselves are essentially stationary. The expanding medium between them carries them apart. This expansion is real. It is measured. It is the reason distant galaxies are redshifted. It is one of the most precisely confirmed phenomena in all of cosmology. Alcubierre's insight was this: if space can expand behind something, and if that expansion carries the something forward, then in principle the something arrives at a destination faster than light could have traveled the same route without violating relativity at any point. The ship never accelerates. The ship never moves through space faster than light. The ship sits perfectly still inside a bubble of flat space-time, while the space around the bubble is manipulated. Space contracts in front, carrying the bubble forward. Space expands behind, doing the same. The net effect is that the bubble, and whatever it contains, travels from point A to point B in a time shorter than light would take, without ever breaking the local speed limit. This is not a metaphor. It is an exact mathematical solution. Alcubierre published it in 1994 in the journal Classical and Quantum Gravity, and he wrote down the metric, the mathematical description of the space-time geometry required, and showed explicitly that it was a valid solution to Einstein's field equations. It did not contradict general relativity. It did not require new physics. It was derived entirely from the existing framework that has described gravity with extraordinary precision for over a century. The geometry of the bubble is specific. Imagine a region of flat space-time, essentially normal physics, surrounding a spacecraft. Outside that region, space-time is curved in a precise pattern, compressed ahead of the bubble in the direction of travel, expanded behind it. The compression-expansion pattern is arranged so that the bubble is pushed forward. From inside the bubble, everything is normal. The passengers are in flat space-time. They experience no acceleration. Now, they are not crushed by inertial forces. They are simply sitting still while the universe around them reorganizes itself to carry them wherever they are going. From outside, the bubble appears to travel faster than light. But locally, at every single point, the speed of light is never exceeded. The ship is not moving through space faster than light. Space is moving, carrying the ship. It is the cosmological expansion happening locally, on demand, directed. When Alcubierre published, the response from physicists was something between astonishment and discomfort. The mathematics was correct. The derivation was valid. The solution existed. And it did not require anything exotic in terms of the equations. But it did require something exotic in terms of the matter needed to produce the geometry. That is where the wall appeared. Not in the mathematics, in the material. To curve space-time in the way Alcubierre's metric requires, you need energy. Specifically, you need energy distributed around the bubble in a very precise pattern. The expansion of space behind the ship requires positive energy. Ordinary matter and energy do this naturally. Ordinary matter curves space-time toward itself, producing attractive gravity, producing the kind of curvature that makes space expand under the right conditions. The compression of space ahead of the ship is the problem. Compressing space-time requires the opposite of what ordinary matter produces. You need something that curves space-time away from itself, something that produces not attractive gravity, but repulsive gravity, something that pushes rather than pulls. Something with, in the language of physics, a negative energy density. This substance is called exotic matter. It is not antimatter. Antimatter has positive mass and falls down in a gravitational field, just like ordinary matter. It is not dark matter, which also has positive mass and attractive gravity. It is something else entirely. A material or field that has negative mass energy, that gravitates in reverse, that would fall upward rather than downward in a gravitational field. In everyday experience, nothing behaves this way. Every material object ever measured has positive energy. Every known field has positive energy density. The universe, as observed, is built exclusively from things that attract each other gravitationally. And yet quantum mechanics, the other great pillar of modern physics, hints that negative energy is not only possible but is already occurring, and constantly, everywhere, at scales too small to directly observe. The Casimir effect is the most famous demonstration. Place two perfectly flat conducting plates extremely close together in a vacuum. Not a few millimeters apart, but nanometers apart. And measure the force between them. There should be no force. The plates are uncharged. The region between them is empty. But the quantum vacuum is not truly empty. It seethes with virtual particle pairs blinking in and out of existence, borrowing energy from nothing for time intervals permitted by the uncertainty principle. Between the plates, the range of wavelengths available to those virtual particles is restricted by the geometry. Outside the plates, the full spectrum is present. This creates a pressure imbalance. The plates are pushed together by a force that should not exist, and produced by the effective negative energy density of the constrained quantum vacuum between them. The Casimir effect has been measured. It is real. The force is small. At micrometer separations, it is comparable to the weight of a grain of sand, but it is there, reproducible, consistent with quantum mechanical prediction. This does not mean we can produce exotic matter in bulk. The Casimir effect produces negative energy in amounts that are genuinely tiny. The gap between what the Casimir effect provides and what an Alcubierre drive would require is so large that describing it as a gap understates it. It is more like describing the distance between a candle and a supernova as a gap. The original energy estimates for Alcubierre's 1994 drive were catastrophic. The bubble geometry he described would require exotic matter with a mass energy equivalent to the mass of Jupiter. Negative Jupiter. A sphere of anti-gravitational material, roughly 140,000 kilometers in diameter, present simultaneously at every point on the bubble wall, maintaining the precise geometry required for faster-than-light travel, held in perfect configuration for the duration of the journey. The engineering requirements for this exceeded not just current capability, but any capability imaginable within any near-term or even far-term technological framework. Jupiter masses of exotic matter is not a technical challenge. It is a category of impossibility. But physics is not static. And the years between 1994 and today have been more interesting than almost anyone expected. Since a theoretical physics problem with an impossibly high energy requirement is not a dead end. It is an invitation. The question physicists asked after 1994 was not, can we build this? The question was, does the drive geometry have to look the way Alcubierre described it? The original bubble was spherical, with a specific distribution of exotic matter throughout the wall. The geometry was elegant, but not optimized. Physicists are extraordinarily good at optimization when the target is clear. The energy requirement for a warp drive is a clear target, and the years that followed saw a systematic effort to find geometries that required less exotic matter to produce the same faster-than-light effect. Harold White at NASA's Johnson Space Center made the first major breakthrough in 2012. he observed that the Alcubierre bubble geometry, while valid, was not the most efficient possible solution. By changing the shape of the bubble from a simple shell to a toroidal, ring-like shape, roughly like a donut rather than a sphere, and by oscillating the bubble wall rather than holding it static, the energy requirements could be reduced dramatically. His analysis suggested that the required exotic matter mass could drop from Jupiter scale to something approaching the mass of the Voyager probe, not Jupiter, a few hundred kilograms. That is still exotic matter, which still does not exist in useful quantities. But a few hundred kilograms of something is a different category of challenge than a Jupiter mass of it. White's result was not universally accepted. Critics argued that the oscillation analysis was incomplete and that the true requirements were higher. But the direction was clear. The geometry mattered. The original estimate was not a lower bound. It was a starting point. In 2021, the direction accelerated dramatically. Eric Lentz, a physicist at the University of Göttingen, published an analysis that reached a conclusion that genuinely stopped his colleagues. A warp bubble might not require exotic matter at all. Lentz's insight was geometric. He found a class of space-time configurations, soliton-like solutions, meaning self-reinforcing wave structures that maintain their shape as they travel, in which the required curvature could be produced entirely by the arrangement of positive energy, ordinary matter, no negative mass required. The energy requirements in his initial solution were still enormous, approximately 10 orders of magnitude beyond current human energy production capacity, but the qualitative shift was staggering. The physics community had spent nearly 3 decades assuming exotic matter was a non-negotiable ingredient. Lentz suggested it was not. The same year, Alexei Bobrik and Gianni Martir published a generalized framework for warp bubble solutions that categorized the entire landscape of possible drive geometries. Their paper introduced the concept of subluminal warp drives, bubble solutions that travel slower than light but that still benefit from the same space-time manipulation principles. These would not provide interstellar travel in useful timeframes, but they would test the underlying physics in laboratory conditions and develop the engineering foundations and potentially point toward the geometries that scale to faster-than-light applications. More significantly, Bobrik and Martir's framework identified which physical parameters most strongly influence the energy requirements. Their analysis pointed toward a class of geometries in which the energy requirement drops by many orders of magnitude compared to Alcubierre's original solution, while remaining within positive energy physics, or requiring only small amounts of exotic energy rather than Jupiter masses. And then, in 2021, something happened that was not theoretical at all. Harold White, now working at the Limitless Space Institute rather than NASA, was leading a lab experiment with an entirely different purpose when he found something he was not looking for. But he found what looked like a warp bubble. The experiment was designed to test whether Casimir cavities, the structures that produce the Casimir effect, could be engineered to create regions of negative energy density, larger and more stable than the simple parallel plate geometry. The goal was to characterize the energy density distribution around a precisely engineered Casimir structure, a small ring of metal, microns in dimension, with carefully controlled surface geometry. The team used an electron microscope to image the energy density distribution around the structure. What appeared in the data was not what they expected. Instead of a simple Casimir-like negative energy region between the plates, the structure showed a distinct geometric pattern in the energy distribution around it. A pattern that, when analyzed mathematically, closely matched the geometry Alcubierre had described for the wall of a warp bubble in 1994. White's team published the finding in a peer-reviewed journal. They were careful in their claims. They did not say they had created a warp bubble. They said they had observed an energy density distribution consistent with warp bubble geometry, forming spontaneously around a specifically engineered Casimir structure, without the application of external energy to produce it. The bubble was not propulsive. It was nanometers in scale. It had no practical application. But it existed in a laboratory, measured by real instruments. The reaction in the physics community was divided. Some physicists dismissed the result as a measurement artifact or a misinterpretation of the data. Others noted that the geometry of the Casimir structure was very specific and that the appearance of warp-consistent energy distributions around it was not easily explained as coincidence. The result has not been independently replicated as of early 2026, which means it remains provisional, but it has not been refuted either. It sits in the literature as one of the most quietly significant experimental results of the decade, either a genuine first glimpse of warp bubble physics occurring naturally at small scales, or an elaborate measurement error that nobody has yet traced to its source. The broader context around this finding is what gives it weight. In the years surrounding White's experiment, a series of theoretical and observational developments began pointing in the same direction from different angles. Gravitational wave astronomy had matured rapidly since LIGO's first detection in 2015. The technique used to detect gravitational waves, measuring the stretching and compressing of space as waves pass through detectors, is, in a fundamental sense, exactly what a warp drive does, not in terms of propulsion, but in terms of mechanism. Both phenomena involve the deliberate or incidental manipulation of space-time geometry. The precision with which gravitational wave instruments now measure space-time distortions, down to fractions of a proton width over kilometers scale baselines, represents a capability that researchers studying warp drive physics have noted is potentially relevant to detecting or characterizing warp-like space-time configurations. This connection is not idle speculation. Several groups working on warp drive theory have proposed that the space-time signatures of warp bubble formation, even at sub-propulsive scales, might be detectable using LIGO-class instruments if the geometry is sufficiently large and sufficiently close. The proposal has not yet been tested. LIGO time is precious and allocated competitively, but the proposal is on the table, peer-reviewed, and taken seriously by researchers who have access to those instruments. In 2023 and 2024, separate papers from groups in Germany, the United States, and Australia developed new approaches to the energy optimization problem using techniques from quantum information theory. The connection between quantum entanglement structures and space-time geometry, originally proposed in the context of the ER equals EPR conjecture, which suggests that entangled particles are connected by microscopic Einstein-Rosen bridges, or wormholes, has spawned a new class of approaches to manipulating space-time that do not require classical matter distributions at all. These approaches are highly speculative and far from engineering application, but they represent a qualitative expansion of the theoretical toolkit available to warp drive researchers, and several of the results suggest that the energy requirements could be reduced by further factors of 10 or more compared to current best estimates. The energy requirement started at Jupiter mass. It dropped to the mass of Voyager. Further reductions continued as of early 2026, The most optimistic estimates from carefully reviewed theoretical work put the exotic energy requirement for a warp bubble, not a fully propulsive interstellar drive, but a warp-consistent space-time configuration, at levels that are still enormously beyond current capability, but not beyond the capability of a sufficiently advanced version of technology that already exists in principle. None of this means a warp drive is being built. None of this means one will be built in this century or the next. The gap between the mathematics permits it and the energy requirements are lower than we thought, and we have built a working prototype, is a gap that has swallowed many beautiful theories. But that gap is measurably, verifiably, year by year shrinking, and the direction of travel is not ambiguous. Before you allow yourself to feel uncomplicated excitement about faster-than-light travel, you need to understand what the physics says happens to everything that is not inside the warp bubble. The problem is the front of the bubble. As the bubble moves through space, it does not travel through vacuum. Space is not empty. It contains hydrogen atoms in diffuse concentrations, averaging roughly 1 atom per cubic centimeter in interstellar space, with higher densities in certain regions, lower in others. It contains photons, light from every star in the galaxy, microwave background radiation from the Big Bang, neutrinos from stellar reactions, cosmic rays from supernovae. All of these things exist in the path of a moving warp bubble. As the bubble contracts space at its leading edge, Particles and photons in the path of that contraction are not simply displaced. They are accumulated. The compressing spacetime at the front of the bubble gathers particles and radiation and concentrates them. The bubble is, in effect, a relativistic snowplow. Everything in its path is swept up and compressed into the leading edge, where it accumulates throughout the journey. Then the journey ends. The bubble dissipates. It cannot dissipate gradually in a controlled way while keeping the passengers safe, because the passengers are inside the flat spacetime region and cannot communicate with the outside. When the bubble collapses, the accumulated radiation and particles at the leading edge are released. They are released forward, toward the destination. And what this means is that a warp bubble arriving at a destination releases a pulse of high-energy radiation directly ahead of its arrival point. The faster the travel, the longer the journey, the denser the regions of space crossed. All of these factors increase the energy deposited at the destination. Early analyses suggested the radiation pulse from a single warp transit across even a fraction of a light year could be sufficient to sterilize any planet in the destination system. Not damage, sterilize, remove surface life. Comparable in energy to a nearby gamma-ray burst. This problem was described in detail by Finazzi, Liberati, and Barcelo in a 2009 paper that received relatively little public attention but was deeply sobering to warp drive theorists. The paper noted that even if the exotic matter problem were solved, even if the energy requirements were manageable, even if the engineering were achievable, a warp drive arriving at a destination with inhabitants, or a destination you wanted to visit and leave intact, would vaporize it. More recent analyses have modeled potential mitigation strategies. Plasma windows at the leading edge, absorbing and dispersing particles before they accumulate. Drive geometries that minimize the accumulation by shaping the bubble wall in ways that deflect, rather than concentrate incoming particles. Pre-emission of the accumulated energy in controlled bursts during transit, rather than all at once on arrival. None of these solutions is fully developed. All of them introduce additional engineering complexity of a kind that makes the exotic matter problem seem straightforward. If there is a second danger that is less physical and more navigational. A ship inside a warp bubble cannot send or receive information from outside it. The bubble is a closed system, in the sense that the compressed spacetime at the leading edge and expanded spacetime at the trailing edge create a horizon, a boundary across which information cannot travel in real time. The crew inside the bubble cannot communicate with ground control. Ground control cannot communicate with the crew. The ship is on a trajectory that was set before the bubble engaged and cannot be altered while it is in operation. If something goes wrong during transit, a miscalculation in the destination coordinates, an unexpected dense region of interstellar medium that disrupts the bubble geometry, and a technical failure in the drive mechanism, there is no intervention possible, not from inside and not from outside. The journey, once begun, completes itself or catastrophically fails. There is no abort sequence. There is no distress call. There is no rescue mission for a ship inside a warp bubble, because by the time any signal from the ship could reach anyone who might help, the ship has already arrived or already ceased to exist. The third danger is the one that theoretical physicists discuss in careful language that tends to obscure its magnitude. Some analyses of warp bubble dynamics suggest that the spacetime distortions involved in faster-than-light travel are sufficiently extreme, and the energy concentrations sufficiently high, that they could in certain drive configurations produce closed time-like curves. That phrase means time travel, not the science fiction version, the technical version. The possibility that a sufficiently energetic manipulation of spacetime could create causal loops, regions where an effect precedes its cause, where the past and future become connected in ways that violate the arrow of time. Stephen Hawking proposed the chronology protection conjecture, the idea that quantum effects would always intervene to prevent the formation of time machines. Essentially, that the universe self-protects against causal paradoxes. The conjecture has not been proven. It has not been disproven. It remains a conjecture. If it is wrong, if faster-than-light travel permits the construction of causal loops, then the implications extend far beyond the physics of travel. They reach into the foundations of causality itself. The most recent concern is more concrete. Certain warp bubble geometries, particularly those involving rapid bubble formation in high-density regions, create conditions that some physicists have modeled as analogous to the interior of a collapsing star. Specifically, the energy concentrations at the bubble walls, if sufficiently extreme, might trigger gravitational collapse to a singularity. Not a controlled formation, not an engineered black hole with known properties, an accidental one. A black hole formed at the destination point at the moment of bubble collapse, in the middle of a star system that was inhabited moments before. These risks are not mentioned to suggest that warp drive research is irresponsible. They are mentioned because understanding the risks is how they get solved. Every aviation pioneer who died in a crash contributed to the safety record that makes commercial flight the safest form of transportation in history. Every engineering failure is a data point. The difference between aviation's early era and the early era of warp drive research is that the failure modes in warp physics are not personal. They are civilizational. The scale of a mistake is not the scale of a crash. It is potentially the scale of a destroyed world. That context changes what responsible development looks like. It makes caution not a conservative preference, but a survival requirement. There is something that deserves a long pause before we continue. The warp drive problem is not new. It has been studied for 30 years. The energy requirements have been coming down for 30 years. The theoretical toolkit has expanded dramatically. Lab experiments have produced suggestive results. And none of this has been front-page news in the way that, say, a new rocket engine test is front-page news. The reason is not that the scientific community is hiding it. The reason is that it is theoretical physics, and theoretical physics does not produce timelines or demonstrations. It produces equations. But there is a pattern in those equations that the people who study them most carefully have begun to notice. And it is not a comfortable pattern. Every time the energy requirements for a warp bubble have been recalculated with better geometry, better mathematical tools, or better physical understanding, the number has gone down. It has never gone up. No refinement of the theory has produced a result saying the original estimate was too low. Every revision has been in the direction of feasibility. The trajectory is consistent, and it is one-directional. This is not proof that a warp drive will work. The trajectory could be approaching a floor, some fundamental minimum energy requirement that is still impossibly high by practical standards. It could be that the most optimistic theoretical results are technically valid but physically unachievable for reasons that have not yet been identified. The history of physics contains many beautiful equations that described real phenomena and still could not be turned into practical technology in any near-term framework. But it is also true that the history of physics contains moments when a consistent one-directional trend toward feasibility eventually reached a threshold. Not gradually, but suddenly. Nuclear fission was theorized for decades before it was achieved, and the gap between first theoretical proposal and first working reactor was shorter than most people expected once the right engineering insights arrived. The transistor was a theoretical possibility for years before Shockley, Bardeen, and Brattain built the first one, and within a decade the entire electronics industry had reorganized around it. Theoretical possibility, once the energy and engineering requirements drop below a threshold, tends to convert to practical reality faster than linear extrapolation would predict. The warp drive is not there yet. It may not reach that threshold in this century, but the direction of the arrow is not toward impossibility. It is toward difficulty. And difficulty has a different relationship with human ingenuity than impossibility does. Meanwhile, the universe has been doing something on its own that is worth considering. The expansion of space, the cosmological expansion that the warp drive concept borrows from, is not a hypothetical. It is happening right now, measurably, at every point in the observable universe. Space is stretching. It has been stretching since the moment of the Big Bang. The rate of that stretching is described by the Hubble constant, which has been measured with extraordinary precision by multiple independent methods. The physics that produces the warp drive solution is not invented physics. It is observed physics. We're running continuously, at cosmological scales, in the universe that already exists. The question is not whether spacetime can be manipulated, It already is, constantly, in the largest possible way. The question is whether it can be manipulated locally, on human-accessible scales, with human-accessible energy budgets. That is a much harder question. But it is not the same question as whether it can happen at all. And there is one more thing that the universe has been saying, quietly, in the data from gravitational wave observatories and high-energy particle experiments and cosmological surveys that deserves to be said clearly. The vacuum is not passive. The quantum vacuum, the ground state of space, the condition of empty space in the absence of ordinary matter has energy. That energy is real, it is measured. It is the source of the Casimir effect and the accelerating expansion of the universe. The cosmological constant, which Einstein introduced and later called his greatest blunder, turns out to be real, a property of empty space itself that acts as a repulsive energy filling all of space-time. The universe, at its most fundamental level, is already doing what an Alcubierre drive needs. Empty space is full of energy, and that energy has the right sign. The question of whether it can be engineered is different from the question of whether it exists. It exists. It fills every cubic meter of space that has ever been observed. The warp drive, in a profound sense, is not asking for something foreign to the universe. It is asking for something the universe already does, applied with precision. In a building at the Limitless Space Institute in Houston, Texas, a small team of researchers is doing something that would have seemed absurd in most physics departments a decade ago. They are building laboratory apparatus specifically designed to test warp bubble physics, not to build a drive, not to achieve propulsion, to measure, at micrometer scales, whether the space-time geometries predicted by warp drive theory can be produced by carefully engineered quantum vacuum structures, and if so, what the relationship is between the engineering parameters and the resulting geometry. This work is funded, it is staffed, it is publishing results. It is being taken seriously by a physics community that as recently as 2010 would have treated warp drive research as too speculative for serious institutional engagement. Yet the shift in institutional attitude is partly a result of the energy estimates coming down. Jupiter mass gets you laughed out of a grant committee, Voyager mass gets you a polite hearing, and the theoretical diversity of the field, the number of independent groups in different countries reaching the same directional conclusion through different mathematical approaches, has given the research a robustness that single-author speculative papers do not carry. The engineering challenges that would exist even if the physics is solved completely are not trivial. They are, in honest terms, at the extreme frontier of everything humanity knows how to do. The first challenge is the production of exotic matter, or alternatively the arrangement of ordinary matter in quantum vacuum structures and configurations that produce the equivalent effect. Current capability to produce Casimir effect, negative energy densities, covers areas measured in square micrometers, with energy densities billions of times smaller than what warp drive geometries require. The gap between laboratory Casimir physics and warp drive energy requirements is not a gap that is going to close by improving existing Casimir apparatus. It requires a qualitative breakthrough in understanding how quantum vacuum states couple to macroscopic space-time geometry. That breakthrough has not happened, but there are theoretical frameworks in which it could happen, and the frameworks are specific enough that experiments can be designed to test them. The second challenge is metric engineering, the problem of controlling the shape of the space-time distortion with the precision required to produce stable, directed bubble propagation without runaway effects. The relevant mathematics is known. The engineering capability to implement it is not. Creating and maintaining a space-time geometry with the precision that warp drive calculations require would demand measurement and control systems that can operate at the quantum gravity boundary, the scale where quantum mechanics and general relativity intersect and where current theoretical physics is least reliable. The quantum gravity problem, the unification of the two great theories of modern physics, is one of the most challenging open problems in all of science. Warp drive engineering is downstream of its solution. The third challenge is the containment and guidance problem. Even if a warp bubble can be created, and maintaining it as a stable configuration against perturbations, the natural irregularities of the interstellar medium, the quantum fluctuations that permeate all of space, requires either extraordinary passive stability in the drive geometry or active feedback control that operates faster than the perturbations it is correcting. Since the bubble propagates at faster than light speeds, and since no information can travel faster than light even inside normal space-time, the feedback control problem has unusual properties. The drive system cannot receive information from the leading edge of the bubble faster than light travel allows. This means perturbation correction must be either predictive, anticipating the interstellar environment ahead of the bubble, or passive, relying on drive geometries that are inherently stable without external control. Predictive guidance requires a complete map of the interstellar medium in the direction of travel, at densities sufficient to identify regions that could destabilize the bubble. We do not have such maps. We have the broad outlines of interstellar density distributions at scales of light years. The fine structure, the density fluctuations at scales of kilometers, which are the scales relevant to warp bubble stability, is largely unmeasured and, at current observational capability, largely unmeasurable. These are not final objections. They are accurate descriptions of where the field is. The honest summary is this: the physics says it is possible. The energy requirements are high but not infinite and are coming down. And the engineering challenges are severe but specific, meaning they are the kind of challenges that can be worked on rather than the kind that represent fundamental prohibitions. The people who work in this field are not dreamers in the pejorative sense. They are physicists who have done the mathematics carefully and found that the mathematics does not say no. They are in the unusual and uncomfortable position of working on something that their own discipline's most fundamental theories say is permitted, while the practical path from theory to hardware remains unclear. That combination, theoretical permission plus engineering obscurity, is not unique in the history of physics. It is, in fact, the normal starting condition for any technology that later became transformative. Imagine for a moment that it works. And not the full interstellar version, not a drive that crosses light years, but a demonstrator. A laboratory-scale warp bubble, centimeters in diameter, that propels a test mass across a few meters of distance faster than a conventionally accelerating equivalent could have crossed the same distance. Unmistakable, reproducible, photographable, something that a graduate student can see on a screen and say, the space-time is doing what the equations say it should. What happens next is not a technical question, it is a human question. Every major threshold in the history of human exploration has required people willing to commit themselves to uncertainty so complete that survival was not among the guaranteed outcomes. Not unlikely, not guaranteed against, simply not guaranteed. The first pilots to fly beyond the sound barrier did not know what the sound barrier would do to an aircraft and a human body. The first astronauts to orbit the Earth did not know whether the Van Allen radiation belts would be survivable. The first cosmonauts to conduct spacewalks did not know whether their suits would hold at the seams where theory and manufacturing met the vacuum of space. In each case, the people who volunteered were not reckless. They were precise. They had calculated the probabilities as carefully as their tools allowed. They had accepted the residual uncertainty as the cost of doing something necessary, and they had decided that the thing was worth it. Not for personal glory, the literature on what motivates extreme risk-takers in scientific exploration consistently de-emphasizes personal glory in favor of something harder to articulate and more durable. A sense that the thing being attempted matters in a way that outlasts the individual. A recognition that someone has to go first. And a feeling, not always rational, not always articulable, that the first person might as well be them. The first crew of a warp flight would face a selection process that makes astronaut training look like a job interview. The physical requirements would be unusual, not the athletic requirements of conventional spaceflight. Warp bubble passengers experience no acceleration. So the cardiovascular and musculoskeletal demands are different, but the requirements for physiological stability in an environment whose long-term biological effects are completely unknown. The quantum vacuum modifications at the bubble boundary produce radiation signatures that no living human has ever been exposed to. The baseline assumption of safety inside the bubble is theoretical. It has not been tested with biological tissue. the psychological requirements would be severe in a different direction. The crew of a warp flight cannot communicate with the outside world during transit. They cannot receive instructions. They cannot call for help. They cannot, in any conventional sense, be supported. They will be in a bubble of flat space-time, traveling through a universe that is moving around them at superluminal velocities relative to their reference frame, cut off from every signal, every voice, every presence that connects them to the human world. The transit for even a nearby destination might last hours, days, or weeks of subjective time, the precise duration depending on the drive, geometry, and route. In conditions of absolute isolation from everything except the other crew members and the instruments in front of them. The psychological profile required for that kind of mission is uncommon. Not courage in the simple sense. Courage is insufficient. The requirement is equanimity in the presence of genuine unknowns with no intervention path, the ability to remain functional, to make precise technical decisions, and to communicate clearly and rationally in a situation where the entire context of normal human existence has been removed and the only available feedback is the data coming off instruments that have never been operated in these conditions before. That profile exists. History has produced people who carry it. They are unusual enough to be rare and common enough to be found. The first warp mission would carry, in all likelihood, a crew of 2 or 3. The size is driven not by the requirements of the voyage itself. A warp bubble can, in principle, carry any mass that fits within its geometry, but by the psychological and operational reality that a crew too small faces catastrophic vulnerability to individual incapacitation, and a crew too large creates the coordination problems that degrade performance in novel and stressful environments. The mission profile would be conservative in the extreme, not Alpha Centauri, not anything near Alpha Centauri. The first warp mission would likely target a destination measurable in light hours or light days, something within the outer solar system or just beyond it, both to minimize the duration of the communication blackout and to minimize the consequences if the bubble collapses unexpectedly. A drive failure at one light day from Earth leaves a crew who can, in principle, survive in their disabled spacecraft and eventually be retrieved, although the retrieval window would be measured in years. A drive failure at 4 light years from Earth leaves nothing that can be reached. Yet the naming of such a mission has been discussed in informal contexts. No official designation exists. The comparison to Kitty Hawk is made often, and it is not wrong. In December 1903, Orville and Wilbur Wright achieved the first controlled, powered flight over a distance of 36.5 meters in 12 seconds. The demonstration proved the principle. The engineering that followed transformed the world within a generation. The warp demonstrator, when it comes, will be the equivalent of that 36.5 meters. Short, fragile, barely controlled. The greatest single step in the history of human navigation since the first human stood at the edge of the ocean and built something to float across it. Before we can talk about what working warp drives would mean for civilization, we have to sit with a problem that the physics raises directly and that popular discussions of warp drives consistently understate. The problem is time, not relativistic time dilation. The slowing of clocks in fast-moving reference frames, which is a solved and well-understood phenomenon. The problem is causality. The problem is that the mathematics of faster-than-light travel does not behave well when you apply it across different reference frames. Here is the issue stated as plainly as possible. In special relativity, the concept of simultaneity, of 2 events happening at the same time, is reference frame dependent. 2 observers moving relative to each other will disagree about whether 2 events that are separated in space happened simultaneously, in sequence, or in which order. This is not a philosophical dispute. It is a mathematical consequence of the structure of space-time. For events connected by signals or objects traveling slower than light, this ambiguity does not cause causal paradoxes. The ordering of cause and effect is preserved across all reference frames, even though the simultaneity of separate events is not. The cause always precedes the effect, in every reference frame, for any signal or object traveling below light speed. For signals or objects traveling at or above light speed, This preservation breaks down. There exist reference frames from which a faster-than-light signal appears to arrive before it was sent, not just simultaneously. Before. This is not a matter of interpretation. The mathematics is straightforward. If you can send a signal from point A to point B faster than light,
and if observers at A and B are moving at sufficient speed relative to each other, there exists a reference frame from which the signal at B preceded the signal at A. The practical implication of this is troubling. It means that two warp-capable civilizations, or a single civilization using warp drives along different trajectories, could in principle use faster-than-light travel to send information or matter back in time. Not accidentally, deliberately. The combination of two faster-than-light trips at the right angles and velocities is, in the language of general relativity, a closed time-like curve, a path through space-time that begins and ends at the same event. Alcubierre knew this when he published in 1994. He acknowledged it in the paper. Alan Everett and others analyzed it in detail in subsequent years, showing explicitly how a network of warp gates could be configured to produce causal paradoxes. Hawking's chronology. Protection conjecture was partly motivated by this exact concern, by the hope that quantum effects would save causality, even if classical general relativity permitted its violation. The conjecture has not been resolved. The physics is genuinely uncertain here, and that uncertainty is not a minor footnote. It is a central feature of the warp drive problem that any responsible discussion must face directly. Here is what an honest accounting looks like. The mathematics of general relativity permits faster-than-light travel, and the same mathematics permits the consequent construction of time machines, whether quantum gravity or some other physical principle prevents. This is unknown. If it does not prevent it, then a working warp drive network is not just a transportation system, it is a causality violation engine. The implications of that are not computable within current physics. They are not computable within philosophy. They are not computable within any framework we possess for reasoning about consequences. A technology that allows effects to precede causes is not a tool. It is a weapon against the structure of reality. That may sound like science fiction. It is, technically speaking, science. The equations are clear. The question is what other equations we are missing that might constrain or prevent what those equations imply. This is not a reason to stop the research. Understanding the constraint, the physics that prevents time travel, and if any, requires understanding faster-than-light travel well enough to test whether the constraint exists. You cannot verify the chronology protection conjecture without building something that approaches the conditions where it would apply. The research and the caution are not in conflict. They are the same thing. Step back from the physics for a moment. Step back from the engineering, the risks, the philosophical hazards. Consider what a working warp drive would mean not for physics but for the species that built it. Distance is the organizing principle of almost everything about human civilization. Geography shaped the emergence of distinct cultures, languages, religions, political systems. The borders of nations are historical accidents of military reach and economic geography. The diversity of human civilization, its richness, its conflict, its creativity, is a product of the fact that human communities developed in relative isolation and then encountered each other over timescales long enough for each to build elaborate distinctiveness before confrontation. The spread of communication technology has been eroding this isolation for 2 centuries. The telegraph, the telephone, the internet, satellite communication, each has collapsed the informational distance between places while the physical distance remained intact. You can speak instantly to someone on the other side of the planet, but you cannot be there in a meaningful sense. The physical world still has its distances. Matter and bodies still take time to move. A warp drive eliminates this last holdout entirely. But the logistics of physical reality would transform faster than any previous technology has transformed them. The entire global supply chain, the ships crossing oceans, the trucks crossing continents, the aircraft crossing time zones, is built around the fact that moving physical goods takes time, and that time costs money. A warp transport system that could move a shipping container from a factory in Asia to a distribution center in Europe in minutes would not disrupt the shipping industry. It would dissolve it. The ships would be obsolete, the ports would be obsolete. The entire infrastructure of global logistics, which employs hundreds of millions of people directly and indirectly,
and represents trillions of dollars of capital investment, would become functionally worthless within a generation.
The disruption would not stop at shipping. Real estate values are fundamentally a product of location, and location is fundamentally a product of distance. The reason a square meter of land in central London costs more than a square meter of land in rural Wales is that proximity to the economic activity, culture, and services concentrated in London takes time and cost to access, and time and cost are constrained by physical distance. Remove the physical distance constraint, and the value of location changes completely. You could live anywhere and work anywhere. The premium on urban centers, which has driven one of the great economic sorting processes of the past century, concentrating wealth in cities while hollowing out rural regions, would evaporate, not quickly, not cleanly, but irreversibly.
But the implications for national borders are more unsettling. Borders are enforced through the physical difficulty of crossing them undetected and the cost of moving large numbers of people or goods without authorization. Customs, immigration control, military exclusion zones. All of these are mechanisms built around the reality that movement takes time, and that time creates windows for detection and intervention. A warp-capable transport that crosses national borders in seconds creates detection and intervention problems that no existing border enforcement framework is equipped to handle. Not impractical problems, impossible ones. If anyone can be anywhere in seconds, the concept of a sovereign territory with controlled access becomes a philosophical aspiration rather than a physical reality.
As the economic implications of eliminating scarcity by distance would also include the elimination of the economic value attached to geographic resource monopolies. Oil fields, rare earth deposits, arable land, these have value partly because they are located somewhere, and getting their output somewhere else requires logistics. Warp transport changes the effective distance between every resource and every consumer to approximately zero. The geopolitical significance of being in close proximity to a major resource deposit, which has driven wars, alliances, and entire foreign policy architectures for centuries, would decline toward irrelevance. There is a version of this that sounds utopian. Global poverty is substantially a function of geography, of being born far from the infrastructure, markets, and in educational institutions that enable economic participation. If warp transport makes distance irrelevant, then geography as a determinant of life outcomes fades. The child born in a remote village has the same access to the same resources as the child born in a wealthy city. Not because the village was transformed, but because the concept of remote was transformed. There is also a version that sounds dystopian. Every existing power structure that depends on geographic advantage, every state whose military power rests on territorial control, every corporation whose market position rests on logistics superiority, every institution whose influence rests on physical concentration, would face an existential challenge simultaneously. The mechanisms through which human societies have organized power, managed conflict, and distributed resources for millennia would face a technology that renders them obsolete faster than new mechanisms could be designed and implemented. The transition between those two versions, between the utopian possibility and the dystopian risk, is not governed by the physics. It is governed by the political, economic, and institutional choices made by the civilization that develops the technology. And the history of transformative technologies suggests that those choices are made badly as often as well, that the benefits are distributed unequally before they are distributed fairly, and that the disruptions arrive before the adaptations. The warp drive would be the most disruptive technology in the history of the species, not because of what it destroys, but because of what it makes irrelevant. Distance has been humanity's organizing principle for as long as there have been humans. A technology that makes distance a matter of choice rather than necessity does not just change transportation, it changes what civilization is. Now take everything above and extend it beyond Earth, beyond the solar system, beyond the comfortable scale of things that human civilization has ever touched. The nearest star system contains at least 3 stars and at least 1 confirmed planet. Alpha Centauri b has a planet in the inner system, detected via radial velocity and debated since 2012. Proxima Centauri, the smallest member of the Trinary, and the technically closest star to Earth at 4.2 light-years, hosts Proxima b,
a planet roughly Earth mass sitting in the habitable zone, the region where liquid water could exist on the surface, and Proxima d, a smaller inner planet. Proxima b receives about 65% of the energy per unit area that Earth receives from the Sun. It orbits a red dwarf, which means it is likely tidally locked, one side permanently facing the star, one side permanently in darkness, and subject to intense stellar flares that could strip atmospheres and bombard surfaces with radiation. Is anything alive there? We do not know. We have no way of knowing from Earth. The instruments that could begin to answer that question are atmospheric spectrometers on telescopes powerful enough to analyze the thin sliver of starlight filtered through Proxima b's atmosphere during transits. Those instruments are being planned, and they do not yet exist. And even when they exist, the answer they can provide is probabilistic, not definitive. A warp ship could answer the question in days. This is not a small thing. The question of whether life exists elsewhere in the universe is the most significant unanswered question in science. Not because it has practical applications in the immediate term, but because its answer determines the context in which every other question about human meaning and purpose is asked. If life is common, if even the nearest star harbors living things, then the universe is not the sterile, silent void that 65 years of radio telescope searches have suggested. The silence that the SETI field has been confronting is not evidence of absence. It is evidence of the communication gap, of biological civilizations separated by distances that make contact impractical at light speed, but trivial at warp speed. If life is rare, if Proxima b is barren, and the next 10 star systems are barren and the ones beyond them are barren, then the warp drive changes the meaning of that barrenness. It transforms the sterile cosmos from a prison into a territory. Every empty world is a potential. Every barren moon is unwritten. The civilization that can travel between the stars freely is not constrained to a single planet with a single biosphere and a single geological timeline. It becomes, in a sense that is difficult to overstate, a multiplanetary, then a multistellar, then a galactic civilization. The timescales for this transition, even with working warp drives, are not human comfortable. And a galaxy 100,000 light-years across, explored at warp speed but still requiring time to survey each system, understand each world, build infrastructure, and establish sustainable presence, is a project measured in centuries at minimum and millennia more likely. No individual human alive today would see it completed. No single government or corporation would oversee it. It would span generations in a way that makes the Manhattan Project look brief and the Great Wall of China look modest. But the beginning is different from the completion. The beginning is a ship, 3 people, a destination 4 light-years away, a journey that takes, in subjective time, some number of days or weeks, depending on the drive configuration. The beginning is a moment that changes everything, not because of what it accomplishes, but because of what it proves. Yes, that the wall is not a wall, that the universe is not locked, that the distance between the stars, which has existed as an absolute prohibition on human ambition for as long as humans have been capable of conceiving of ambition, is a solvable problem. That moment, not the arrival at Alpha Centauri, but the departure from Earth, and the return and the confirmation that both happened and that both were survivable, is the moment from which everything else follows. Not immediately, not within a generation, but inexorably. There is a sentence in Alcubierre's 1994 paper that has been quoted many times and understood relatively rarely. He wrote, "Within the bubble, the metric is perfectly flat, and the passengers would suffer no accelerations whatsoever." That sentence contains something more than a technical specification, and it contains a description of what it would feel like. Inside a warp bubble, from the perspective of the passengers, nothing is happening. The instruments on the ship read normal. Gravity is normal, set by whatever artificial gravity system the ship uses, just as in conventional space travel. There are no tidal forces, because the geometry of the bubble insulates the interior from the curvature outside. There is no sensation of motion, because there is no motion, technically speaking. The space-time containing the ship is moving. The ship is not. If you looked out the windows, you would see the universe compressing ahead of you and expanding behind you. a visual distortion that would make the starfield ahead look blue-shifted and compressed toward a central bright point, and the starfield behind look red-shifted and expanding toward the edges. The visual effect has been modeled. It is dramatic and strange, and not like anything in human visual experience outside of this specific context, but it would be real-time visible. Stars, galaxies, the actual universe, seen from inside a space-time manipulation device in real time. That image, human beings looking out a window at a universe being reorganized around them, sitting in a quiet room with coffee and instruments while the stars rearrange themselves, is not a science fiction image. It is the image that falls out of the mathematics. It is what the equations describe when you ask them what the experience would be. The passengers would not know they were moving. By every local measurement, they would not be moving. Yet the clocks on the ship would run at the same rate as the clocks on Earth. No relativistic time dilation inside the bubble because there is no relative motion between the ship and its local space-time. A journey to Alpha Centauri that covers 4.2 light-years at 10 times light speed would take the passengers roughly 5 months of subjective time. When they arrived, and the bubble dissipated, and they were back in normal space-time, they would be 5 months older. Back on Earth, 5 months would also have passed. No time dilation, no twin paradox, no aging discrepancy. This is profoundly different from relativistic travel at near light speed, where time dilation means the travelers age less than those left behind. Warp drive does not compress subjective time for the travelers. It compresses actual travel time for everyone, equally. The ship moves quickly through the universe's real time, not through a relativistic shortcut in proper time. If you left Earth on January 1st and traveled to Alpha Centauri and back at warp speed, arriving home on March 1st of the following year, your family on Earth would also have experienced 14 months. You would be the same age. The conversation you left would not have aged in your absence. The world you return to would be the same world, slightly older. Not the science-fictional scenario of returning to find everyone you knew had died of old age. This detail matters more than it might appear. Relativistic travel at near-light speeds offers speed at the cost of connection. The travelers age slowly. Everyone else ages normally. The faster you travel, the more completely you are severed from the civilization you left. A ship traveling at 99% of light speed to Alpha Centauri and back would age by months, while Earth aged by years. A ship traveling at 99.999% of light speed would age by days, while Earth aged by decades. The faster you go, the more completely you return to a world that has moved on without you. That is not a minor inconvenience. It is an existential separation. Every conventional, faster-than-light workaround has this problem in some form. Warp drive does not. The bubble moves space. It does not stretch time. The passengers who leave Earth come back to the same Earth, older by exactly the time the journey took, surrounded by people who have also aged by exactly that time. The social and psychological continuity that conventional relativistic travel destroys is preserved. You go, you come back, everything is still there. That is not just technically significant. It is what makes interstellar civilization possible, rather than just interstellar travel. A civilization can only span the stars if the stars are connected. If every journey severs the traveler from their home by decades or centuries, then the stars are visited but not inhabited in any continuous sense. The warp drive, and only the warp drive among the solutions that current physics permits, connects the stars without severing the travelers. It makes the galaxy not just reachable, but livable. The history of the warp drive idea does not begin with Alcubierre in 1994. It begins with a mode of thinking that has recurred throughout the history of science, whenever a seemingly absolute barrier has been examined closely enough to find its assumptions. Hermann Oberth, in the 1920s, it was told that rockets could not work in the vacuum of space because they had nothing to push against. The objection seemed obvious to everyone who raised it, and Oberth's response, that rockets push against their own exhaust, and exhaust does not require an external medium, was too counterintuitive for many of his contemporaries to accept. He was correct. Oberth's foundational work on rocketry, dismissed by many as impractical fantasy, led directly to the rockets that put humans on the moon within his lifetime. Mach and others argued, with good physical reasoning from within the framework of 19th century physics, that heavier-than-air flight was impossible. The arguments were coherent. The framework was incomplete. The Wright brothers were not physicists. They were bicycle mechanics who built things until things flew. The sound barrier was, until 1947, widely believed to be an actual physical wall, not just a region of increased drag and turbulence, but a genuine boundary that aircraft could not cross. The name barrier was not metaphorical. Chuck Yeager crossed it in October 1947. Within a decade, supersonic flight was routine. Within a generation, it was commercial. In each case, the seemingly absolute barrier was not disproven. The framework that made it seem absolute was replaced by a more complete framework in which the barrier did not exist, or existed in a different form, or could be approached from an angle that the original framework had not considered. Alcubierre did not disprove Einstein. He found a door in Einstein's equations that Einstein had not noticed was there. The people who study this problem today are doing what Oberth did, what the Wright brothers did, what Yeager did. They are taking seriously something that seems absurd from within an incomplete framework and working within the complete framework. The full apparatus of general relativity, quantum field theory, and the growing connections between them, to find what the complete framework actually says. It says the door is there. The question it cannot yet answer is whether anyone can open it, with what key, at what cost, and what is on the other side. Those are hard questions. They are engineering questions, which are different from physics questions in a specific and important way. Engineering questions have answers that can only be found by building things and seeing what happens. Every civilization in history that encountered a new means of travel was transformed by it. Every single one. At the degree of transformation correlated with the degree of change in what was reachable. The development of ocean sailing ships transformed European civilization by making the Americas and Asia reachable. The steam engine transformed industrial civilization by making inland resources reachable. The railroad transformed continental civilization by making cross-country markets reachable. The aircraft transformed global civilization by making every city on Earth reachable within a day. Each transformation followed a similar arc. The technology arrived first in the hands of those with resources: states, wealthy merchants, industrial combines. The early benefits accrued primarily to those who deployed the technology first. The disruption it caused fell disproportionately on those least able to adapt. And then, over generations, the technology became ubiquitous. Its costs fell, its benefits spread, and the civilization that emerged on the other side was so different from the one that had existed before that the transition looked, in retrospect, like the boundary between eras. The warp drive, if it works, would produce this pattern on a scale that makes the entire previous history of transportation technology look preliminary. The first warp-capable ships would belong to whoever built them, states or corporations or some combination with the resources to fund a project at the frontier of physics. The early missions would be governmental or quasi-governmental, following the model of the early space age. The destinations would be chosen for scientific and strategic purposes: the nearest stars, the most promising planets, and the territories most useful for understanding what is out there and most relevant to establishing a presence. The strategic implications of first-mover advantage in warp drive technology exceed any previous first-mover advantage in the history of military and economic competition. The nation or entity that controls warp transport before others do does not merely have faster ships. It has the ability to move people, resources, and military assets anywhere in the solar system and eventually anywhere in the stellar neighborhood before any competitor who lacks the technology can respond. The military applications are not subtle. A defensive position becomes irrelevant if the adversary can arrive from any direction in minutes. A supply line becomes irrelevant if logistics is instantaneous. The entire art of warfare, which for the past century has been organized around the problem of projecting force across distance over time, collapses when the distance-time relationship is no longer fixed. The race for warp drive is therefore not merely a scientific competition. It is a strategic competition of the first order. Whoever gets there first does not just win the race. They change the rules of every competition that follows. This understanding has begun to penetrate institutional thinking in ways that are not yet reflected in major public funding streams, but that are visible in the background of conversations happening in defense research communities, in space policy documents, and in the strategic planning arms of nations that have identified technology leadership as a survival variable. Yet the alternative to competitive development is coordinated development, an international framework that treats warp drive technology as a shared civilizational project, like the International Space Station, but for the physics of faster-than-light travel, rather than a national strategic asset. Such a framework would require a level of international trust and institutional coordination that the current geopolitical environment makes difficult to imagine. But the alternative to imagining it is a competition with stakes so high that the first crossing of interstellar space becomes an act of dominance rather than an act of exploration, and whatever civilization emerges on the other side of that transition carries the shape of its founding moment into the future. The shape of the founding moment matters. The United States went to the moon in the context of a military competition, and the space program it built reflected that context: focused, powerful, risk-tolerant, nationalistic, and ultimately unable to sustain itself after the competitive context dissolved. A warp program built in the same context might achieve the technical milestone faster, but the civilization it creates on the other side of the stars might not be one that anyone who chose it clearly would choose. There is a different way to think about who decides. Not nations, not corporations, not the institutions that currently hold the resources and the authority and the inertia. The people who will ultimately shape what warp travel means are the ones who use it. Not the first mission, not the engineers, not the generals and the ministers and the CEOs, but the ordinary people who eventually book passage to somewhere that has never been reached before and arrive somewhere new with everything they care about and whatever they were able to carry. That is who decided what the Americas meant. Not Columbus, not the Spanish court. The millions of people who crossed the ocean for their own reasons, carrying their languages, their seeds, their tools, their gods, their grudges, their hopes, and their diseases into a world that neither they nor the people already there had prepared for. The stars will be decided the same way, by whoever gets there, carrying whatever they bring, doing whatever they do. The physics just has to cooperate. There is a question that the warp drive idea makes more uncomfortable than it was before. For 65 years, humanity has been listening for signals from other civilizations, pointing radio telescopes at nearby stars, cataloging candidate signals, processing billions of candidate hits through automated filters, and arriving at a total of 0 confirmed extraterrestrial transmissions. The silence has been documented in detail, and in that documentation sits one of the most disturbing facts in science. The universe has had 13.8 billion years and trillions of stars to produce neighbors who would make themselves detectable, and as far as every instrument ever built can determine, it has not. The Fermi paradox has many proposed resolutions. Life is rare, intelligence is rare. Technology is self-destroying. Civilizations go quiet as they become more sophisticated, and civilizations expand into dimensions or substrates that are invisible to radio telescope searches. The universe is young enough that we are among the first. Each of these resolutions is internally consistent, and none is fully satisfying. The warp drive adds a new dimension to the problem. If warp travel is physically possible, if the mathematics permits it and the engineering is merely difficult rather than fundamentally prohibited, then any civilization that existed long enough to develop warp capability would not merely be broadcasting signals. It would be moving. It would be showing up at stars. It would be reorganizing stellar environments in ways that are visible across astronomical distances. A civilization with millions of years of warp capability would, in all probability, have spread across the galaxy. It would not look like a civilization in any recognizable sense. It would look like a galaxy-spanning structure, detectable through its engineering, its modification of stellar environments,
its distinctive heat signatures, its organized distribution of matter and energy. The Milky Way does not look like that. It looks like a galaxy that has never been touched by engineering at any scale above the planetary. No Dyson spheres, no stellar engineering, no organized structures that couldn't be explained by natural astrophysical processes. The galaxy appears, to every instrument pointed at it, to be the product of physics and chemistry operating without intelligent intervention for its entire 13 billion year history. If warp drive is possible, and the galaxy should have produced civilizations capable of it, then either the civilizations did not survive to develop it, or they developed it and are somehow hidden, or warp drive has a property we don't understand that prevents civilizations from spreading even after they develop it. The third option has received less attention than it deserves. We noted the dangers of the front-end radiation pulse, the impossibility of communication during transit, the risks of causality violation. Each of these could represent not just engineering challenges but civilizational traps. A civilization that develops warp drive and uses it carelessly could sterilize every destination it visits with the radiation released at bubble collapse. A civilization that uses it to navigate the causal structure of spacetime carelessly could destabilize its own timelines. A civilization that becomes dependent on warp transport could become strategically vulnerable to whoever controls the drive technology. None of these are guaranteed outcomes. They are risks. But the history of transformative technology is a history of civilizations encountering risks they did not anticipate at the scale that the technology operates. And the warp drive operates at a scale that includes the fabric of space-time itself. The Fermi paradox, combined with the theoretical existence of warp drive solutions in general relativity, suggests either that something beyond the engineering is preventing the use of this technology at civilizational scale, or that civilizations do not typically survive to the point where they could use it. The second option is the Fermi paradox's grimmer face, the great filter, in whatever form it takes. It reliably terminates civilizations before or shortly after they develop the capability to become interstellar. If the filter is ahead of us, if something that typically destroys civilizations is something we have not yet encountered, then the development of warp drive technology could be either the precursor to our passing through the filter or the instrument of the filter itself. A technology that can carry the consequences of a civilization's errors to other star systems carries those errors at the speed at which the drive operates. Problems that were once contained to a single planet become problems that span a stellar neighborhood. The capacity for civilizational expansion and the capacity for civilizational catastrophe scale together. The silence in this light is not just a mystery, it is a warning. Not because it proves the worst case, but because it is consistent with the worst case in ways that require explanation, and no comfortable explanation has yet been found. Part 17. The weight of it. There is a moment that comes in the contemplation of any very large thing when the mind cannot hold it and the feeling arrives instead. You can count to 1,000 and keep track. You cannot count to 1,000,000,000 and keep track. At some point, the number becomes a feeling. And the feeling is not the number. The feeling is the recognition that the number exceeds what can be felt, and that the reality behind the number exceeds even that. The observable universe spans 93 billion light years. It contains 2 trillion galaxies. It has been running its processes for 13.8 billion years. That is the stage. The stage is real. Hence, every galaxy in the Cosmos Web survey catalog exists, with its hundreds of billions of stars, each a furnace running nuclear reactions that began before the Earth formed. Every star in every galaxy is doing what our Sun does, fusing hydrogen to helium, pouring radiation into space, maintaining a planetary system against the entropy that will eventually cool it to silence. And around some of those stars, no one knows how many, the estimates run from millions to trillions. Something that could be called life is doing whatever it does in whatever form it takes on a world nothing like ours. None of this can be visited. Not by any technology that exists or is likely to exist in any near-term framework. The observable universe is sealed, not by impossibility, but by distance, by the finite speed of light and the expansion of space carrying most of it permanently beyond reach.
the most that any plausible version of warp drive technology could deliver in any time frame a civilization could plan for, is the immediate neighborhood, a few hundred light years in every direction. Maybe, over centuries, a few thousand. The rest of the 93 billion light years would remain as it is now, present, visible, real, unreachable. But the few hundred light years surrounding our sun contains, conservatively, tens of thousands of stars. And those tens of thousands of stars have, statistically, around 100,000 planets. And some of those planets are inhabitable zones, and some of those worlds have liquid water. And some, we do not know how many, well, we cannot know until we go, have something on them that is more than chemistry. That is what is at stake in the warp drive problem, not the technology. The technology is secondary. What is at stake is whether this species, on this world, gets to find out what is actually out there, whether the universe that produced us gets to be known, at least in its local sample, by the things it produced, whether the 300,000-year experiment of human consciousness examining its surroundings gets to examine surroundings that require more than a single solar system. The drive equations sit in textbooks. The energy requirements are declining. The labs are running experiments. The theorists are publishing. The data is accumulating in a direction that everyone who reads it carefully recognizes as meaningful. And somewhere in the mountain ranges of a future not yet determined, in a facility that does not yet exist, built by institutions that have not yet been founded to solve a problem that has not yet been solved, a machine is going to do what the mathematics says is possible. It is going to compress space. It is going to create, in a small volume, a bubble of flatness in a curved universe, and it is going to move that bubble from one point to another faster than light could have crossed the same distance. It will be fragile. It will be tiny. It will last for moments. But it will be real. And the universe, which has been waiting 13.8 billion years for something inside it to try this, will do nothing unusual. The stars will keep burning. The galaxies will keep expanding. The cosmic web of dark matter will go on holding everything in its invisible architecture. Because the universe does not know or care what any specific collection of atoms inside it is attempting. But the atoms will know. The atoms that once lived inside a dying star, that were scattered into a cloud, that condensed into a world, that organized into life, that organized into language, that organized into mathematics, and that finally organized into a machine capable of doing what those atoms never could when they were only scattered and burning. Those atoms will know. The nearest star is 4.2 light years away. The mathematics says we can get there. We begin. There will be a day. Nobody knows when. Oh, but the mathematics and the trend lines point to a day that is real, rather than hypothetical. When a ship leaves the vicinity of Earth and the instruments tracking it register something that has never been registered before. A space-time distortion. Small at first. Local. Contained. And then the distortion deepens. And the ship is gone. And the instruments that were tracking it lose the signal, not because the ship failed, but because the ship is now inside a region of space-time that is moving faster than the signals that would announce its position can escape from it. The tracking stations will not know, in that moment, whether the ship is alive or destroyed. They will not know whether the bubble held or collapsed. They will not know whether the passengers are sitting calmly in flat space-time watching the stars blue shift ahead of them, or whether something went wrong in the first seconds and there is nothing left to track. They will wait. The waiting will be the most significant waiting in the history of the human species, not because the mission's outcome is uncertain. Uncertain outcomes have been faced before, from the first ocean crossing to the first moon landing, but because what is being waited for is not just the safety of the crew and the success of the mission. What is being waited for is confirmation that the universe is what the mathematics says it is. That the door Alcubierre found in Einstein's equations is a real door. That space is what the field equations describe, and not something less, not something closed, not something that forbids its own inhabitants from exploring it. If the ship comes back, if the distortion reappears at the coordinates where the destination was calculated to be, and the instruments register the bubble collapse, and the telemetry begins to flow again, and the crew's voices arrive over the radio, doing their best to sound calm and failing somewhat, then the number changes. Not the number of galaxies, not the number of stars, not the number of potentially habitable worlds. Those numbers will stay what they are: vast, incomprehensible, real. The number that changes is the number of those worlds that are reachable. Before the ship returns, that number is 1. After the ship returns, that number has no upper bound that any current mathematics or any current imagination can assign. The universe is 93 billion light years across. We are made of the same material that built it, and the same equations that describe its structure describe the machine that might eventually let us see all of it. Hold your hand up, look at it again. The iron in your blood was forged in a star. The carbon was scattered by a supernova. The oxygen was produced by a generation of stars that lived and died before the sun ignited. You are not looking at your hand. You are looking at the universe, looking at itself through the particular arrangement of matter that became you. The nearest star is 4.2 light years away. That is not a wall, that is a destination. The mathematics of general relativity permits faster than light travel. The energy requirements are real, significant, and declining. The engineering is beyond current capability, and the direction of current capability is toward it. The risks are severe, specific, and the kind that require solving rather than the kind that require stopping. The universe has been running the relevant physics for 13.8 billion years. We have been studying those physics for roughly a century. We are not at the end of what is possible. We are at the very beginning of what the equations say is permitted. And the equations, for all the ways they have constrained human ambition, have never once been wrong. It's been